Think about it, the invisible engines of our modern world, the algorithms that power everything from your morning search results to potentially life-saving drug discoveries and even our understanding of climate change.
Right. And for all their sophistication, the truly revolutionary ones often feel like these um, flashes of human genius, serendipity almost.
Exactly, which really begs the question, could we actually automate that spark, that moment of algorithmic invention?
That's precisely the challenge Google DeepMind has taken on with AlphaEvolve. It's a fascinating AI coding agent.
Powered by Gemini, right?
Yes, they're Gemini models, and it's designed to autonomously create and crucially refine algorithms. But what's really groundbreaking, I think, is its potential to discover fundamentally new ways of solving problems, not just following existing blueprints.
Okay, hold on. An AI that's not just writing code based on instructions I give it, but actually designing the logic from the ground up.
That's the idea.
For anyone tracking large language models, this feels like, well, a monumental shift. We've seen them go from text generators to, pretty decent code writers.
Sure, like Copilot and tools like that.
But AlphaEvolve seems to be leveraging them for something much deeper, genuine problem discovery. It's this really interesting fusion of LLM smarts and evolutionary computation.
Yeah, and what's particularly insightful here is that transition. We're moving from seeing LLMs as maybe intelligent assistants,
Like super-powered autocomplete.
kind of, yeah,
Yeah.
to potentially creative collaborators in research and development. AlphaEvolve really hints at a future where AI can help us uncover computational methods we might never have thought of ourselves.
Could this actually redefine AI's role in innovation? I mean, that's the big question, isn't it?
It certainly presents a compelling case. It forces us to rethink the boundaries.
And crucially, it's not some black box spitting out answers, right? They're emphasizing this show your working principle.
Absolutely. That means AlphaEvolve generates code that we humans can actually understand, read, and ideally learn from.
That transparency feels essential, not just for building trust, which is huge, but also for enabling us to learn from the AI's discoveries, maybe even improve upon them.
Exactly. So in this deep dive, we're going to unpack the core principles behind AlphaEvolve. We'll explore the foundations, evolutionary computation, and how LLMs fit in.
Okay.
Then we'll examine AlphaEvolve's architecture, how it actually works is pretty impressive achievement so far in math and the real world, and sort of place it in the broader AI landscape.
Right. The goal is to give you, the listener, a clear understanding of this exciting step forward and what its potential impact might be.
Let's do it.
All right, let's get into those foundational ideas then. You mentioned evolutionary computation. For those who might have a general sense, but maybe not the specifics, what are the core concepts? What makes it so powerful for finding new algorithms?
Okay, think of it like Darwin in the digital age. Seriously. Evolutionary algorithms, or EAs, take inspiration directly from natural selection.
Survival of the fittest, basically.
Pretty much. They operate on a population of candidate solutions. In this context, those solutions are algorithms, or maybe just parts of algorithms.
So you've got this diverse pool of potential ways to solve a problem, all competing.
Precisely. And to guide this competition, you need a judge. That's the fitness function. It's absolutely crucial. It quantifies how good each potential solution is.
So it translates the goal, like speed or accuracy, into a score?
Exactly. A quantifiable metric the AI can actually work with. The better a solution performs according to this metric, the higher its fitness score. Simple as that.
Makes sense. So you rate your pool of solutions. What's next?
Then comes selection. Just like in nature, the solutions with higher fitness scores are more likely to be chosen to, well, reproduce, to contribute to the next generation of potential solutions.
Okay, and how do they contribute? How do you get new algorithms from the good old ones?
Through genetic operators. These are the mechanisms that introduce variation, allowing the system to explore new possibilities, not just stick with what it knows.
Like mixing and matching the genes of the successful algorithms.
Exactly. The main ones are crossover, or recombination. That's where you combine elements, bits of code, essentially from two parent solutions to create offspring. The hope is they inherit the best characteristics of both.
Okay, combining good ideas. What else?
And then there's mutation. This introduces small, random changes to a single solution. It might seem minor, but it's vital for maintaining diversity in the population.
Ah, so it prevents the system from getting stuck in a rut, exploring only variations of the current best.
Precisely. It helps explore totally new areas of the solution space, things you might not reach just by combining existing good ideas.
So it's this iterative cycle. Evaluate, select the best, mix and mutate them, evaluate again.
That's the core loop. Generation after generation, this process refines the solutions, ideally pushing them towards something highly effective, maybe even optimal.
And this works well for complex stuff.
Yeah, EAs are particularly good for tackling complex problems, especially those with multiple objectives you need to balance, or where the space of possible solutions is just enormous and difficult to search exhaustively.
Okay, so that's the evolutionary engine. Now, how does genetic programming, or GP, specifically apply this to writing code?
Right. Genetic programming is a specialized type of EA. Here, the individuals in the population aren't just abstract solutions, they are actual executable computer programs. The whole point is to evolve a program that solves a specific task.
So instead of tweaking numbers or parameters, you're literally evolving lines of code.
Correct. And traditionally in GP, these programs are often represented as trees, syntax trees.
Okay, like breaking down a math formula.
Exactly. Think of a hierarchy. Internal nodes are operations like addition, multiplication, maybe logical operators. The leaf nodes at the bottom are the terminal's input variables or constants. So like max, xx less 3y, could be a tree with max at the top.
I see. And the branches lead down to the calculations xx and x plus 3y.
Precisely.
And how do you do crossover and mutation on these trees? Seems tricky.
It can be. Crossover might involve picking a branch, a subtree from one parent program, and swapping it with a branch from another parent.
Okay.
And mutation could be changing an operator node, maybe swapping a plus for a minus, or even replacing an entire subtree with a new randomly generated one.
That sounds like it could easily break things. You could end up with a lot of code that just doesn't run or makes no sense, right?
That's definitely one of the big challenges with traditional GP. Those rigid tree structures can be hard to manipulate effectively. You often get syntactically invalid offspring. Plus, setting it up requires a lot of upfront work.
Like defining what functions and variables it can even use.
Exactly. You need significant domain expertise just to define the initial building blocks. It's hard to know what the essential ingredients should be, which, kind of hints at why a more flexible approach might be really beneficial.
Which brings us neatly to large language models. We know they're good coders now. How do they go beyond just assisting programmers to actually driving this kind of algorithmic discovery?
Well, LLMs have shown this incredible ability, as you said, to understand and generate code. That's because they've been trained on just massive amounts of code and text.
Billions of lines of code, right?
Billions, yeah. So they can translate between languages, explain code, help debug. The basic process is understanding the prompt, finding relevant patterns in that vast training data, and then generating new code. We see this in tools like GitHub Copilot already.
Right, those are great assistants. But how does that skill translate into discovering entirely new algorithms? That feels different.
It is different. And that's where this newer field, LLM genetic programming, or LLM-GP, comes in. It's trying to combine the code intelligence of LLMs with the search power of GP.
Okay, getting the best of both worlds. How does it work differently from the tree-based GP we just talked about?
A really key difference is how the code is represented. In LLM-GP, you often just treat the code as, well, plain text, like a normal code file.
No trees.
No rigid trees. The system relies on the LLM's built-in understanding of syntax and meaning, which it learned during training.
Interesting. So how do you do crossover and mutation then if your genome is just a block of code text and you're using an LLM?
You basically reimagine those operators using prompts. For crossover, you might give the LLM two parent code snippets and ask it to, say, recombine these two programs meaningfully, or create a new program incorporating the best ideas from these two.
So you're relying on the LLM's understanding of programming concepts to do the blending.
Exactly. And for mutation, you'd give it a single program and prompt it to improve this code, or modify this function to be more efficient, or refactor this snippet.
That sounds way more flexible than just swapping tree branches. What are the upsides and downsides?
The potential advantages are pretty big.
Yeah.
You tap into that huge knowledge base the LLM has, potentially leading to much smarter, more context-aware variations. And LLMs are generally good at generating syntactically correct code, which helps avoid wasted effort.
Okay, but what are the catches?
Well, LLMs can still be a bit of a black box. It's not always clear why they made a certain change. Their output can be very sensitive to how you word the prompt. Prompt engineering is key. They also require a lot of computation. And, importantly, they can still generate code that's subtly wrong or buggy, or reflects biases from their training data. It's not magic.
So basically, LLM-GP uses the LLM as this really sophisticated engine for generating code variations. It's guided by natural language prompts instead of direct, fiddly manipulation of code structures.
That's a great way to put it. The LLM acts as an intelligent mutator and recombiner, using its grasp of semantics and context. It's a big shift from the purely syntactic shuffling of traditional GP. And this leads us right into AlphaEvolve, which is a really advanced example of these ideas in action.
Okay, foundations covered. Let's dive into AlphaEvolve itself. What's its main goal, the core mission, the philosophy behind it?
The big mission for AlphaEvolve is the autonomous design, and importantly, the continuous optimization of advanced algorithms. And they're aiming broadly, both for abstract math problems and for very practical, real-world computing challenges.
So keywords there are autonomous design and continuous optimization.
Absolutely. Letting the AI take the lead in creation and then constantly refining what it comes up with.
And that show your working principle is still central.
Very much so. Just like its predecessor, FunSearch, AlphaEvolve is built to generate human-readable code. And that's not just a nice-to-have feature. It seems core to their approach.
Why is that so important, do you think?
Well, it builds trust in what the AI produces. It lets us actually understand the logic, see how it arrived at a solution. And that opens the door for humans and AI to collaborate on refining these discoveries even further. The details come from DeepMind's own explanations, their blog posts and papers.
Got it. Okay, let's get into the mechanics. How does this AlphaEvolve engine room actually work? What are the steps in its algorithm crafting process?
It runs in this iterative evolutionary cycle. It kicks off with something called a prompt sampler. This isn't just asking a generic question. It dynamically puts together instructions for the Gemini LLMs.
Dynamically, what does that mean?
It means the prompts can incorporate insights from the process itself, like it might include code snippets from high-performing algorithms found in earlier cycles, or relevant mathematical context, or specific code structures it wants the LLM to think about. The goal is to guide the LLM smartly.
So it's feeding the LLMs information based on what's already working well, learning as it goes.
Exactly. Then comes the code generation phase. And here, they do something clever. They use an ensemble of Gemini models, specifically Gemini Flash and Gemini Pro.
An ensemble. Why use two different models? What's the strategy?
It's a smart division of labor. Gemini Flash is built for speed and efficiency. So they use it for broad exploration, casting a wide net, generating lots of diverse initial ideas quickly.
Okay, speed for exploration, then what about Pro?
Once Flash surfaces some promising candidates, they bring in the more powerful Gemini Pro. Pro's better at deeper reasoning, so it's used for the heavy lifting, in-depth refinement, critical analysis, and really optimizing those promising algorithms identified by Flash.
Ah, so Flash finds the rough diamonds, Pro polishes them.
That's a good analogy, yeah. Guided by those tailored prompts, the LLMs act as these advanced evolutionary operators. They perform mutations by iteratively improving existing code. Maybe some high-level crossover, too, by combining concepts. But the focus really seems to be on that step-by-step iterative improvement. It's a constant loop. Rewrite, improve, based on feedback.
Okay, so Gemini generates some code. How does AlphaEvolve know if it's actually any good? Or even correct?
That brings us to the absolutely critical step. Automated evaluation. This is non-negotiable. Once Gemini generates a program, it's automatically tested, rigorously.
Tested for what? Just that it runs?
No, much more than that. It's checked for correctness. Does it actually do what it's supposed to do? It's executed. And then it's scored based on objective metrics specific to that problem. That could be accuracy, speed, memory usage, whatever matters for the task.
So it's not just about avoiding errors, but about performance against defined goals.
Precisely. This rigorous evaluation is vital. It grounds the LLM's creativity in cold, hard, empirical reality. It stops it from just generating code that looks plausible, but doesn't actually work well, preventing those hallucinations we sometimes see with LLMs. This was key in FunSearch, too.
And the results of these tests feed back into the system.
Directly back. The scores and the code itself go into the evolutionary framework.
Which is managed where? How does it keep track of everything?
There's a central database. This database stores all the evaluated programs and their performance scores. But it's more than just storage. It is the evolutionary algorithm's brain, in a sense.
How so?
It maintains the population of solutions, and it uses all that performance data to decide what to do next. Which programs are the most promising? Which ones should be fed back into the prompt sampler to guide the LLMs for the next generation? This is how it balances exploring brand new ideas versus exploiting the good ones it's already found.
That strategic use of Flash for exploration and Pro for refinement really does seem like a clever way to handle that classic exploration versus exploitation trade-off in search.
It really is. And I suspect we'll see more of this kind of approach using ensembles of specialized AI models in future complex systems. It makes a lot of sense.
Oh, yeah.
But again, I have to stress the importance of that automated evaluation, the fitness function.
It's the anchor.
It's everything. It's the objective judge. Without a clear, formal way to measure if a solution is good, this whole LLM-driven evolutionary approach just wouldn't work. It really underscores why they need to pick problems where solutions are formally verifiable, where you can write that evaluator. Evaluability is key.
Now, you mentioned AlphaEvolve builds on earlier DeepMind work. Can you place it in context with things like FunSearch, AlphaTensor, and AlphaDev? How does it relate?
Yeah, it's definitely the latest step in this ongoing quest at DeepMind for AI-driven discovery. FunSearch from 2023 was a really important precursor. It also paired an LLM, PaLM2 in that case, with evaluation and evolution.
Right, for math and CS problems.
Exactly. The user provided the problem, the evaluator, maybe a starting seed program, and the LLM was prompted with the best results so far to generate new code, new functions mostly. AlphaEvolve takes that concept and scales it up dramatically.
How so?
It can handle whole code bases, not just functions. It works across multiple programming languages. It optimizes for multiple objectives at the same time. It's moved beyond evolving just functions to evolving complete programs, complex things like constructor functions, search heuristics, even entire optimization pipelines. It's a much bigger scope.
Okay. And what about AlphaTensor and AlphaDev? They used reinforcement learning, not LLM centrally, right?
Correct. AlphaTensor back in 2022 used RL techniques similar to AlphaZero to find faster algorithms for matrix multiplication. AlphaDev in 2023 also used RL to discover better algorithms for basic things like sorting and hashing, even right down at the assembly language level.
So AlphaEvolve represents a shift towards LLMs.
It seems to be a significant shift in emphasis, yes. LLMs are now central to the discovery process. And interestingly, AlphaEvolve has actually managed to outperform the specialized AlphaTensor on some specific matrix multiplication tasks, which is pretty telling.
So is the takeaway that LLMs plus evolution might be a more general or flexible approach than pure RL for this kind of discovery?
It's looking that way, potentially. While RL is incredibly powerful when you can clearly define the game of finding an algorithm, LLMs seem to offer more flexibility and maybe raw creativity for generating diverse candidate solutions, especially when you don't know the optimal structure beforehand. The evolution part then provides the critical selection pressure.
So LLMs for the creative generation, evolution for the rigorous selection.
That combination seems really promising for tackling a wide range of problems with generality and creative power. It's a fascinating evolution in DeepMind's own methodology.
Okay, let's talk results. What has AlphaEvolve actually achieved? We've heard the theory, now let's see the performance. What are the breakthroughs?
The results are genuinely impressive, spanning both pure mathematics and very practical real-world applications inside Google. In math, one of the headline results is discovering new algorithms for matrix multiplication.
A fundamental operation in computing.
Absolutely fundamental. Specifically, AlphaEvolve found an algorithm for multiplying 4x4 complex matrices using only 48 scalar multiplication.
And the old record was?
49. Set by Strassen way back in 1969.
Wow. Breaking a 50-year-old benchmark. That might sound like just one multiplication saved, but for something so basic, the ripple effects could be huge, right?
Exactly. Improving fundamental operations like that can lead to significant speed-ups across countless applications that rely on them.
Incredible. What other mathematical frontiers did it tackle?
It was turned loose on over 50 open problems in areas like analysis, geometry, combinatorics, number theory, a real spread.
And how'd it do?
Remarkably well. It managed to rediscover the existing state-of-the-art solutions in about 75% of those cases, so matching human expert-level performance on challenging problems.
Okay, matching is impressive. Did it ever beat the best?
Yes. In about 20% of those open problems, it actually found solutions that improved upon the best previously known ones.
Can you give an example?
A great example is the kissing number problem in 11 dimensions. The question is, how many identical spheres can you arrange so they all touch a central sphere of the same size without overlapping?
Okay, I can picture that in 3D. 11D is harder.
Exactly. It's a classic hard geometry problem. AlphaEvolve found a new configuration allowing 593 outer spheres in 11 dimensions. This set a new, improved lower bound for that specific problem.
That's seriously advanced math. What about the real-world stuff? How is it being used inside Google?
The impact there has been tangible and significant. For example, Google runs its massive data centers using a cluster management system called Borg.
Right, orchestrating all those machines.
AlphaEvolve was tasked with finding better scheduling heuristics for Borg. It autonomously discovered a heuristic that was, surprisingly, quite simple but very effective.
And the result.
The result has been an average 0.7% continuous recovery of Google's compute resources worldwide.
0.7%. That doesn't sound like much until you consider Google's scale.
Precisely. At their scale, that translates to the equivalent compute power of hundreds of thousands of machines being freed up or used more efficiently.
And this isn't theoretical that software has been running in production for over a year now.
That's a massive efficiency gain. Huge cost savings, huge resource savings. Any other examples?
Yes, it's also made contributions to hardware design. It proposed an optimized rewrite of a Verilog circuit that's a language used to design chips for matrix multiplication on their TPUs, their tensor processing units.
Optimizing the hardware itself.
Yeah. The optimization involved removing redundant bits from the calculation while ensuring it still produced the correct results. This could lead to smaller chips using less power. Interestingly, they noted this particular optimization had actually been found before by humans using other methods. So AlphaEvolve independently rediscovered a known optimization. It's actually reassuring in a way. Shows it's finding real, valid improvements.
It does. And it's even being used to accelerate AI development itself.
How so? AI optimizing AI.
Exactly. It achieved a 23% speed up in a critical computational part, a kernel used inside the Gemini models themselves. That improvement is estimated to cut about 1% off the total training time for those huge models.
Which saves immense amounts of time and compute resources again.
Absolutely. And it also sped up the flash attention kernel, which is vital for many modern AI models, by up to 32.5% in some cases, by optimizing its low-level code representation. So it can work at different levels of the software stack.
These wins are across such different areas: pure math, data center operations, hardware design, AI training. It really paints a picture of a general-purpose algorithm discovery tool.
It does, and you can see how these successes could create a kind of flywheel effect within Google. Well, recovering compute resources saves money and energy. Faster AI training accelerates research. These benefits can be reinvested into building even better AI, better discovery systems.
And fundamental breakthroughs like faster matrix multiplication could benefit everyone eventually.
Exactly. It's this virtuous cycle. AI optimizing the tools and infrastructure used to build more AI. That could potentially speed up progress dramatically.
So AlphaEvolve is clearly a major player, but it's probably not the only approach people are exploring for AI-driven algorithm discovery, right? What else is out there?
That's right. It's a hot area. There are other interesting methods. For instance, something called deep distilling. It's quite different. It tries to use neural networks to learn the essence of solving a problem from data and then distill that knowledge into simpler, human-readable symbolic code.
So less direct search, more learning and summarizing.
Kind of, yeah. Bypassing the explicit evolutionary search. And AlphaEvolve also fits into this broader trend people are calling agentic AI for science.
Meaning AI systems that act more autonomously.
Yeah, AI agents that can reason, plan, make decisions to help with scientific tasks. AlphaEvolve is like a very specialized agent focused purely on algorithm discovery within that bigger picture.
Okay. And you mentioned another system earlier, EvoTune. How does that compare? It also uses LLMs in evolution, doesn't it?
It does, yes. EvoTune is another approach combining LLMs and evolutionary search, but it has this really intriguing twist. It uses reinforcement learning.
Huh. RL comes back into the picture, but how?
It uses RL to continuously refine the LLM itself while it's doing the search.
Wait, so the LLM isn't just a static tool generating code, it's learning to be a better generator during the search process.
That's the core idea. EvoTune runs in cycles. First, an evolutionary search phase where the LLM generates algorithms that get evaluated, performance data is collected. Then an RL training phase.
And what happens in the RL phase?
The LLM's internal parameters, its weights, get updated based on the feedback from how well its generated algorithms performed. It gets rewarded for generating better scoring programs. So the LLM literally learns to become a better algorithm proposer over time for that specific type of problem.
That's fascinatingly different from AlphaEvolve, where the Gemini ensemble seems to be fixed during a run, right? AlphaEvolve uses smart prompting and selection, but the models themselves aren't changing mid-discovery.
Exactly. AlphaEvolve and FunSearch use the LLM more like a powerful but static generator. EvoTune aims for the LLM's policy, its strategy for generating code to dynamically improve during the search itself.
Wow. Meta-learning for algorithm discovery. Has EvoTune shown good results?
The paper presenting it reported that it outperformed a FunSearch-like baseline on several classic optimization problems, things like bin packing, the traveling salesman problem.
How did it outperform?
It found programs with higher scores, meaning better solutions, and got closer to the known optimal answers for those problems. The reward signal for the RL just comes from the evaluation scores of the programs it generates. So it's directly learning what kinds of code lead to good scores.
So we have AlphaEvolve using this powerful ensemble and clever evolutionary strategy, and EvoTune focusing on making the LLM itself learn to be a better searcher. Two really interesting paths converging on the same goal.
It really is. EvoTune's approach, where the LLM learns how to propose algorithms better, could potentially lead to systems that become highly specialized and incredibly effective for certain problem classes. It's like the AI is learning the specific landscape of good solutions in that domain.
It definitely suggests a future where AI isn't just making discoveries, but actively refining its own discovery processes. Super
It's a
interesting.
very exciting direction.
So, stepping back, what's the bigger picture here? What's the broader significance and the likely future path for systems like AlphaEvolve?
Well, the potential is huge. Beyond the math and Google internal applications, think about fields like material science, drug discovery, climate modeling, sustainability. Anywhere complex problems can be framed algorithmically and where you can automatically verify if a proposed solution works.
If you can write that fitness function.
Exactly. If you can define success objectively. Looking ahead, we'll obviously see continued improvements in the LLMs themselves, Gemini 2.5 Pro, whatever comes next, which will directly boost systems like AlphaEvolve.
And will researchers outside DeepMind get to use it?
They're working on accessibility. There's an early access program for academics mentioned, and they've been quite open, sharing the math results via a public Google Colab notebook, for example. Transparency seems important to them.
User interfaces, too, presumably, making it easier to interact with.
Development on user interfaces and better human-AI collaboration methods is definitely underway. That's a big focus.
But you mentioned that verifiability bottleneck earlier. Can you expand on that limitation?
Right. That's a key challenge right now. AlphaEvolve, as we discussed, relies heavily on that automated evaluation. The generated programs have to run, and their performance needs to be scored objectively.
Which works great for math proofs or code speed.
Yes, but it's harder for problems with fuzzy goals, or where success is more qualitative. Think early-stage drug discovery, is this molecule promising? Or designing a new material, does it feel right? Current versions struggle there.
So for those fields, we need better ways to evaluate the AI suggestions.
Precisely. Maybe more sophisticated ways to keep humans in the loop for evaluation, or perhaps even AI systems that can act as reliable proxy evaluators, though building trustworthy AI evaluators is its own massive challenge. That evaluation part needs to evolve too.
Okay. So boiling it all down, for someone maybe working with LLMs or just following the field closely, what are the main takeaways from AlphaEvolve's story so far?
I'd say there are several key things. First, the sheer power you get from combining LLM generation with evolutionary search. That synergy is undeniable. Second, the absolute necessity of robust, automated evaluation. Garbage in, garbage out applies just as much to the evaluation function.
Can't discover good solutions if you can't recognize them.
Exactly. Third, we're seeing LLMs really expanding their role. They're not just coding assistants anymore. They're becoming potential discovery engines.
A fundamental shift.
Fourth, the details matter. The architectural choices, like using model ensembles or dynamic prompting, make a big difference in performance. It's not just about having an LLM.
Right. Then fifth?
And finally, the value of transparency that show your work idea. Generating understandable code is crucial for trust, debugging, and truly collaborative human-AI progress.
AlphaEvolve really does sound like a landmark development. It's giving us this fascinating preview of how AI might accelerate science and technology in the future.
It absolutely is. It's a powerful demonstration of combining different AI techniques, and it really points towards a future where human ingenuity and AI discovery capabilities work together, much closer together.
We encourage everyone listening to check out the DeepMind resources if you want to dive even deeper. The blog post, the paper, the Colab notebook for the math stuff, lots to explore.
Definitely worth it. And it leaves you thinking, doesn't it? What fields will be transformed next by this kind of approach? How will humans best work with these systems? What completely new capabilities might emerge as LLMs get even better at reasoning and discovery?
It's more than just a tool, isn't it? It feels like a symbol of a shift in how knowledge itself might be advanced.
I think that's right. It's a powerful symbol of a future where AI and human intellect team up to push the frontiers faster than ever before.